In 2005, the electronics market was defined by a race to make devices smaller and sleeker. The Archos AV700 went the other direction. It was a bulky, heavy portable media player that required two hands to hold. Tech reviewers at outlets like CNET panned the device. They criticized the screen for being cheap and flickery, locked to a low resolution of 480 by 234 pixels. The interface was frustrating, with an ugly menu system and tiny, unlabeled buttons. Yet, if you look past the consumer tech reviews, you find the AV700 showing up in unexpected places. In 2010, the official equipment manifest for Deathpop, a professional heavy metal recording studio, listed the AV700 sitting directly alongside their mixing desks and microphones. Even stranger, in a 2019 peer-reviewed marine biology paper published in Frontiers in Marine Science, researchers cited the exact same consumer media player as a core component of their data collection methodology on the open ocean. The AV700 failed as an entertainment toy, but the specific hardware choices Archos made, the same physical dimensions and input connections that consumers hated, actually turned it into a highly capable piece of industrial equipment. The dominant consumer devices in 2005, like the Apple iPod, were designed strictly for playback. They pulled digital files from a computer and pushed them to a screen or a pair of headphones. The Archos approach relied on open input-output architecture. Instead of restricting the hardware to playback, the engineers built in analog pathways to receive incoming signals. By equipping the device with standard analog composite video and audio inputs, they enabled it to record raw, continuous feeds directly from external sources. The screen became less about watching movies and more about monitoring a live data capture. It paired this input capability with an internal hard drive up to 100 gigabytes in size, housed entirely inside a portable unit with a built-in battery. Open hardware architecture allows technology to outlive its manufacturer's intended purpose. By removing restrictions on incoming signals, the hardware functions as a high-capacity bucket for any raw data stream. To understand why the AV700 was so useful to professionals, we have to look inside the casing at the hardware pipeline. An incoming analog wave enters the AV pod. An analog-to-digital converter translates the continuous voltage into digital data. Next, a hardware encoder compresses the bitstream, writing it directly to the hard disk. Unlike closed systems where DRM software blocks recording, the AV700 applied no restrictions. In engineering, a system built to sample real-world physical conditions and convert them into digital numeric values is called a data acquisition tool, or DAQ. By providing an unobstructed, untethered path from an analog input jack straight to a high-capacity hard drive, Archos inadvertently engineered a highly efficient, portable DAQ. This specific hardware capability solved a major physical constraint in audio engineering during the late 90s and early 2000s. For years, the industry standard for capturing master tracks in the studio or out in the field was the digital audio tape, or DAT machine. DAT machines relied on highly complex moving parts. The rapidly spinning gears pulled fragile magnetic tape across delicate reed heads. Any dust, humidity, or mechanical friction could cause tape dropouts, permanently destroying unrecoverable master recordings. This is the exact vulnerability Deathpop Studio eliminated by integrating the Archos AV700 into their equipment rack. They used the AV700 to record uncompressed stereo WAV files, specifically PCM audio, directly through the analog inputs. The signal went straight to a solid-state buffer and then to the hard disk, bypassing mechanical tape entirely. This created an immediate logistical advantage. Instead of manually digitizing a physical tape in real time after a session, the engineer could simply plug the AV700 into a PC via USB and drag the master files directly into their editing software. In a professional recording environment, eliminating the risk of mechanical failure points made a consumer MP3 player functionally superior to dedicated, expensive tape decks. That same raw data capture capability solved an entirely different set of physical challenges in 2008 on the Black Sea. Due to decades of massive nutrient runoff from surrounding river systems, the northwest shelf of the sea experienced severe eutrophication. By the 1990s, the resulting algal blooms had choked off the oxygen, creating a hypoxic dead zone spanning 50,000 square kilometers. This map shows the historical extent of Filifora, a habitat forming red algae on the shelf. A 2019 study targeted this area to map its partial recovery. Documenting this required biologists to visually survey a massive polygon across the ocean, reaching depths of 122 meters. Traditionally, marine mapping of this scale demands heavy infrastructure. Researchers would need a fragile topside PC server rack on the boat, a setup highly vulnerable to saltwater corrosion, physical shock, and requiring massive power generators. The researchers faced a strict logistical constraint. They needed a cheap, battery-powered method to digitize hours of incoming analog video from the seafloor without relying on heavy computer infrastructure on a small surface vessel. This graphic plots their methodology. Across the summer of 2006 and the spring of 2008, the team navigated to dozens of individual sampling stations scattered across the Northwest Shelf. At each station, they deployed a towed benthic imaging sled. The sled carried an underwater analog video camera and was dragged slowly across the ocean floor. As the sled moved, the camera generated a raw video feed, sending the signal up a 100-meter tether. On the boat, the tether plugged straight into the Archos AV700. The device acted as the terminal endpoint, receiving the continuous analog feed in real time. As the footage arrived, the AV700 utilized its onboard hardware codec to compress the incoming analog signal into digital DivX files on the fly. It executed this process perfectly in a wet, mobile environment. The internal battery provided up to 4.5 hours of continuous video recording, and the 100-gigabyte hard drive offered enough capacity to capture the expedition without needing external power. An obsolete consumer device successfully acted as the critical data bottleneck, converting a massive subsea analog environment into portable digital files. These maps are the direct output of those files. By extracting frames from the AV700's video recordings, researchers plotted the exact locations where the Phylophora algae had returned. By overlaying a counting grid on the recorded video, they extracted highly granular data. This chart details the specific percentage cover levels of the algae at each station, allowing for direct statistical comparison against the historical 1966 benchmarks. This precise ecological mapping stands in sharp contrast to the consumer reviews from 2005 that called the device an ugly, frustrating media player. The flickery, low-resolution screen that infuriated consumers trying to watch movies was completely irrelevant to the scientists. They didn't need the screen to look good. They only needed the hardware pipeline to accurately encode the files so they could analyze the data on a high-resolution PC monitor later. A piece of hardware's true value depends entirely on the metric of its user. For a commuter, it was a heavy, poorly designed entertainment toy. For a researcher, it was an incredibly efficient data acquisition tool. The industrial afterlife of the AV700 highlights a specific philosophy in hardware design that is increasingly rare today. Modern devices are tightly controlled, closed ecosystems. They are designed to restrict external inputs, lock users into proprietary software, and prevent raw, open data capture. Open input and output standards remain essential for grassroots scientific and industrial innovation. When engineers can patch signals directly into a storage drive without hitting a software wall, they can solve complex logistical problems in the field using affordable equipment. Hardware longevity is never dictated by the manufacturer's marketing department. It is guaranteed by the absolute freedom of its inputs.